So next, before we move on to the physics of spin, so I want to describe in detail the Stern-Gerlach operator. But before we do that, let's discuss something else. So far, we have discussed the eigenkets of the SZ operator. So I want to now know, suppose that we are dealing with a spin half particle. Now, what are the eigenkets, say, of an arbitrary spin operator? Okay, so for SZ, we have denoted them to be plus and minus. So means that we want to find out what the eigenkets of this operator is in terms of plus and minus. So I won't do the general calculation. The general calculation will be set in an assignment that is coming to you soon. But we are taking this vector n to lie in the, say, YZ plane. Okay. So suppose this is my YZ plane and these are the axes. So this is my axis. This is the y-axis and this is the z-axis. And this is the vector n, the unit vector n, and it makes an angle theta with the z-axis. So what we have done so far is we have taken theta to be 0. Okay, we have been doing the calculation, finding out the eigenvectors of the SZ operators. Now we want to find out the eigenvectors of this general operator. Okay, so what is n? N is going to be 0 sine of theta cosine of theta, right? Do you agree?
Yes, sir.
Okay. So we want to denote the plus eigenvalue of the n dot s operator by the eigenvector by this thing. So this means that this is the plus half eigenvalue of this, and theta means that it is labeling this n vector in this way. This is our notation. So we want to express this in terms of the bases that we know and love, the plus minus bases. So these are the eigenbases of the SZ operator. Okay, so this is the vector we want to find. So let's look at the eigenvalue equation. So the eigenvalue equation is n hat dotted with s acting on plus theta is going to give me plus half plus theta. So now we can write the left-hand side. We know what s is, right? We work this out shortly. So n dot s is going to be cosine the half, because remember that S is a set of 3 vectors where the first vector is half sigma 1, second vector is half sigma 2, third vector is half sigma 3. And let me remind you what the Pauli matrices are. Sigma 1 is real, 1, 1. In the off diagonal, sigma 2 is imaginary. So the thing about the Pauli matrices is that all the minus signs are facing inside. So for example, if you're like not sure if the minus sign should be here or here, Well, if the minus sign was up here, then it would be facing outside. But here it's facing inside. Similarly, if the minus sign was here, it would be facing outside. So it's facing inside. Anyway, that's just my mnemonic. So if I do this, then this thing just becomes, because our n vector, the zeroth, the first component is 0, so this guy is not going to make a contribution. So this is going to be cosine of theta minus I sine of theta, I sine of theta minus cosine of theta. So this is the left-hand side, and this thing is going to be AB, and then right-hand side is half AB. So this is our eigenvalue equation. So this gives us two equations. The first equation is A cosine of theta minus I of B sine of theta is equals to A. The second equation is IA sine of theta minus B cosine of theta is B, right? See, this thing is equals to times this. Okay, and all the halves factor out. So this is equation 1 and this is equation 2. So equation 1, we can solve it. We can actually do the whole thing from equation 1. So equation 1 tells us that, if we divide both sides by A, then I get cosine of theta minus I B by A sine of theta is equal to 1. And this I can write it as minus IB by A is 1 minus cosine of theta divided by sine of theta. So B over A is I times 1 minus cosine of theta divided by sine of theta. But sine of theta is 2 sine theta by 2 cos theta by 2, and 1 minus cos theta is 2 sine squared of theta by 2. So one of these guys cancel here, 2 cancels out, so I get B over A is I sine of theta by 2 cosine of theta by 2. So let's choose A to be cosine of theta by 2. And let's choose B to be I sine of theta by 2. Then you can verify that 2 is satisfied, okay? So I'm going to leave that as an exercise. Show. Okay. And then, thus we have that our state plus theta is cosine of theta by 2 plus I sine of theta by 2 minus. Now let's just make sure that this is normalized. So this is going to be, this will be cosine squared of theta by 2. There won't be any cross terms because these are orthonormal. And of course, there we see that they're normalized. These guys are normalized, so this is sine squared plus cosine squared is 1. Okay? Okay, so any questions about this?
Sir, I'm not sure how we got the matrix cos theta minus I sine theta. Could
Sure,
you
yeah.
put this again a little bit?
Yeah, so let's look at that. So we want, this is our eigenvalue equation.
Mm-hmm.
So this is our eigenvalue equation. and n is a vector which is 0, sine of theta, cosine of theta, right? And S is a set of three matrices, half sigma 1, half sigma 2, half sigma 3. So if I evaluate n dot S, I get 0 times half sigma 1 plus n1 times the n2, sorry. This should be,
Yeah, I got it now. Okay.
yeah, you got it.